especially it's revolutionized this area that I've talked about, which is generalized linear mixed models. So all my examples will be in that area, but it's a very general method that's really changed the way models can be estimated. Anything we do before this? We just kind of jump in and start talking? Is that how it works? Anybody have any questions or anything we should do before I get started? Okay, well, let's start with a quiz, which I think I put into the online material, and this is meant as a review of what I talked about a few weeks ago, because I know you've seen a lot of stuff since then. So let's get back up to speed on that stuff. I'm going to share my screen. Take me a second to remember how to do this. Everybody see a quiz? Okay. So these are just some questions I want to talk through. It's a little bit, I think this might be a little bit nicer to have a chance to think about them rather than me just talking through them. So this first one, write a Poisson generalized linear model. What are its three components? So maybe I ought to back up even a little bit before that. What's the whole purpose of generalized linear models? Why were they developed? What kinds of problems were they developed for?
Fitting non-normal data.
Yeah, fitting models to non-normal data. Any kind of non-normal data?
Exponential family.
Good, exponential family. So one of the ways to think of generalized linear models is that they're how we do data analysis with exponential families. If all you have is the distributions, you can't do data analysis, by which we mean estimating treatment effects and time trends and adjusting for covariates and clustering, all that stuff. So that's what the class of generalized linear models does. So if you write a Poisson generalized linear model, I realize it's kind of tough to talk through the equation, but what are the three things we need to specify for any generalized linear model?
You gotta have an outcome and a link and some predictors.
Good, those are the three pieces. So by outcome, I want to say outcome distribution. So in this case, the outcome distribution will be Poisson. The link function, what is a link function link?
The linear predictors to the mean of the outcome.
Exactly. So there's a mean of the outcome, which is kind of a physically observable thing, right? The mean, you just take the average of your outcome values. If they're binary or Poisson, it's okay, just take the average. So that's a physically observable quantity. The covariates, the linear predictor contains all the covariates, the treatments, the time trends, all that stuff. So yeah, exactly, that's what it links. And let's see, yeah, and then the third part is the systematic part, or the linear predictor. So here you go. And by the way, I'll post this, I'll send this to Matt. Maybe I already sent it to him, I can't remember, but I'll send it to him and he'll post this, so no need to write all this stuff down while we're talking. So here's the Poisson, there's the outcome distribution. The mean of the Poisson has to be positive, and the exponential function keeps it positive. That's one practical thing. That's just another practical thing the link function does. Partly it puts you on a nice scale. So for a Poisson, how do we interpret the betas? How do you use the betas in a sentence?
Relative change.
Sorry, I just didn't hear that.
Relative change.
Yeah, relative change, in other words, a factor change. So the outcome changes by a factor. For Poisson, that's sometimes called a rate ratio. The Poisson mean is a rate of events per unit time, and so the rate ratio is a factor change. Okay, everybody good with that? Any questions on a Poisson generalized linear model? Okay. What general method? So we have to estimate. When I talk about estimation in this model, what are we estimating? Back up here, what are we estimating? Some of these are, okay. There's really nothing else. The X's are known, the Y's are known, so the only thing left is the betas. And remember, that's why we do regression, is to estimate those betas. Those are our time trends and our treatment effects. Okay, so by fitting the model or estimating the model, that's what I mean. What's the general method of estimation and inference we use for these models? Okay, for those of you in theory who took theory last year, you would have spent a fair bit of time second semester on a very general method of estimation. Okay, that was maximum likelihood. Okay, so maximum likelihood is as soon as you have a probability model, you can max it, you can write down the likelihood, you can maximize it. It might be hard to maximize it. It might be numerically hard to find the maximum of the likelihood, but you can still do it. It's there. I mean, it might have multiple maximums, okay, but it's maximum likelihood. So that's what I was thinking of. Why can't we use least squares? We use least squares all through regression. Why can't we use it here? Okay, the answer to this is actually kind of explains why linear regression is so overwhelmingly important in statistics and why it was developed so much earlier. If the model's linear, and by that I mean linear in the betas, then we can use least squares. And that's a good, efficient way to do it. This model is not linear, right? How can you see that instantly? Well, there's the exponential function, right? So immediately, this part, the linear predictor is by definition, right? Linear predictor, that's always linear. But as soon as you've got a nonlinear link function in there, the model's not linearly, the outcome's not linear related to the predictors, so we can't use least squares. That's why we need something more. We have, and in this case, we have maximum likelihood. Any question on that? And by the way, the reason I'm talking about this now is because what I'm going to talk about in a few minutes is an alternative to maximum likelihood that works better in a lot of more complex cases. Okay. We also had an algorithm that we used to get the maximum likelihood estimates. And we were able to construct it because of the exponential family. We have so much structure there. Anybody remember that? Okay, it was a version of least squares, but we had to do some work on it. We had to do do some weighting, and the weighting was partly the nonlinearity and partly the non-normality. So we had to wait for both of those things. It's calculated iteratively weighted least squares algorithm. And the reason it's the nonlinearity of that model that causes all the trouble. Okay, any question on that?
Hey, Gary.
Yeah.
If you really wanted to, could you use least squares and have it give you an estimate? It would just be a terrible estimate. Because there's still like, in a dichotomous outcome, you still have like some difference in the dichotomous outcome, but they'd all be like values of 1, right?
Yeah, that is exactly correct. You could still get estimates of the betas. They just would not be good estimates. In that sense, they wouldn't be efficient meaning they would be more imprecise than they needed to be. Remember all that stuff about efficiency or asymptotic relative efficiency and consistency, stuff like that? You would have estimates that were not very good in that sense. But in fact, when we start the iteratively related least squares algorithm, the usual starting value is the least squares estimates. So you calculate the least squares estimates, and then the problem with the weighting is that the weights depend on the betas, but you don't know the betas. And so you get terrible estimates. Then you use those to calculate weights, and you get slightly better estimates. Use those new estimates, calculate new weights that give you slightly better estimates, and you keep going in that circle until you converge. Okay? Yeah, exactly. Great question. Hey, what else here? So again, the goal today is to come up with to talk about another estimation method. Okay, anybody remember what over dispersion is? Okay, what's the one fact you remember about a Poisson distribution? I don't know what you remember. I can tell you the one fact I remember about a Poisson distribution. There's two facts actually. The mean has to be positive, and
The mean and the variance are the same.
exactly, the variance is equal to the mean, okay? Well, that's not going to be flexible enough for data analysis, right? You wouldn't use a normal distribution. It's like being told you should analyze you should do your multiple regression using a normal distribution with variance equal to 1. You would never even think of doing that. It's kind of the same thing here. So for Poisson, we need another parameter. Somehow we need to get another parameter in that we can independently control the variance separately from the mean. And so over dispersion means the variability. Like if you made a histogram of your data, if you took just take the mean and take the variance, okay? If they're different, that says you've got over dispersion or under dispersion. Over dispersion means the variability is greater than you'd expect from a Poisson. Okay, we talked about 3 methods to include over dispersion in analyses. Anybody remember what those were? Or one of them?
Negative binomial.
Good, negative binomial. So that means, how do we construct that? That means we take a Poisson distribution and make the mean of the Poisson be random, be a gamma random variable drawn from a distribution with that mean, okay? So it just moves, for every subject, it puts a little bit more variability or possibly a lot more variability into its mean, okay? So that means that's where the over dispersion comes from. So we can just come up with, you can just find a distribution that has and the negative binomial has 2 parameters. One of them controls the variability, one controls the mean. So it's exactly what we're after. What's the second method?
Quasi-Poisson.
Good, quasi-Poisson or quasi-likelihood, that specifies a scale parameter. It's not actually a probability distribution, so we can't use maximum likelihood, but similar methods have been developed. Quasi-likelihood, that whole class of things that's developed to fit those models. So scale parameter, if it's bigger than 1, that's over dispersion. Less than 1 is under dispersion. Okay, what's the third method?
Additive error.
Good, we can just come up here to this Poisson and put a plus E sub I, a plus epsilon sub I up here. And again, what is it? The net effect of that is that for every subject, it moves the mean around a little bit, puts a little additional variability, and that additional variability is the over dispersion. Okay, so we've got those 3 methods. Let's see if yeah, okay, so over dispersion, variance is greater than the mean. We can make the mean random with a gamma, which gives us a negative binomial. We can make it, for binary, you can use beta binomial. You can add a normal error to the linear predictor, or you can use quasi-likelihood of the scale parameter. Each of these has pluses and minuses. I'll go through them really quick because this isn't the main topic here, but One of the big advantages of the negative binomial approach is that you've got a closed form likelihood, closed form density and likelihood, which means you don't need to use numerical integration. You still may need to use optimization, but you don't need to use numerical integration. Adding the normal error is nice because it's very flexible. We can use all our normal tools that, you know, the clustering and autoregressive AR1, probably we're going to do all that stuff. Problem is it requires a numerical integration, which is a lot harder numerically. Quasi-likelihood is nice because it's the only one of these three that can model under dispersion as well as over dispersion. The downside of that is it doesn't have an actual probability distribution, so you can't say plot densities, get probabilities, simulate from the model, things like that. Okay, any questions on this? Okay, give 3 models for with over dispersion in the Poisson generalized linear model. Okay, these are, I'm not going to go through these. These are exactly the 3 that I just talked about. I just wrote the equations here. So negative binomial has a mean that's the same, e to the x prime beta. By the way, I just got this question from somebody I work with about, they were trying to use some other approaches, and I kind of tried to sell them on negative binomial because it has a really nice interpretation. Interpretation of the betas is exactly the same as in the Poisson model. Their rate ratios, there's nothing new there. You just have this additional parameter out here that models variability. Okay, quasi-Poisson, you specify the mean, and then you separately specify the variance, and then here's your additive linear predictor here. Okay, anything there? Okay, final question here. Remember the serial data we talked about? Each family had a bunch of people in it, and then each person was measured multiple times over time. So there were repeated measurements and also family members clustered in each family. So we had 2 kinds of correlation there. For your homework last time, you didn't model any of those because you didn't have the tools. Now let's talk about adding clustering. Say we wanted to model, instead of just the one child, say we want to model all the people in the family. And you want to put in covariates for whether the person's a parent or a kid or a girl or whatever. How could you incorporate that clustering back up, say, in this model here? How would you incorporate the clustering? How would you communicate to the model that some members are from the same families?
Can you add a random intercept?
Exactly. We would just put a plus epsilon ij up here, and we're in business, okay? Now, when I say we're in business, well, yes and no. It's easy to write down the model. It's hard to figure out how to fit it. And that's where down here in this model, okay, this is the model we're talking about now, except that we have this for independent data. Now we have to have an EIJ for clustered data, subject J in family I. Now we have to do numerical integration. And if we have over dispersion also, now we have to do numerical integration at 2 levels. That's where the numerical stuff just breaks down, and we really cannot do that. So here's the model we would use. Now we have I and J for person J and family I. So there's notice here. These are really, okay, so this is a key thing here. The E has an IJ on it. That means each subject gets an error. That's what gives us over dispersion. The use of I is the cluster, that's per family I, and that's what gives us the clustering in a family. So if use of I is large, every person in that family likes cereal. If U sub I is small, every person in that family doesn't like cereal, okay? Whereas if the EIJs, if EIJ is large, it's that one person that gets an extra boost. They just happen, for factors we can't measure, to like cereal, okay? So the subscripts are important to keep track of here. You've seen that all with Matt anyway, just kind of reinforcing it. Okay, any questions here? Okay, so this is the model, this is the kind of model that if the E's and U's are independent, normally distributed, this is a kind of model that could not be fit by maximum likelihood. There's just, the numerical estimation is just too difficult. What I'm going to talk about now, Markov chain Monte Carlo, is a way to estimate this model. Totally, completely different approach, but it gives us estimates of the model parameters, which is in this case of the betas and the variances of the E's and U's. Okay, that's where we're headed now. Any questions on this review stuff? Sorry, I don't know how to, oh, actually, let me do that. Let me get rid of my email so you don't have to. Okay, I'm going to switch over to the set of notes. And these notes are posted. They were posted, I think Matt posted them yesterday. So I'm going to share again. Okay, so overview of Markov chain Monte Carlo and its use in statistics. These are all Bayesian. In order to use Markov chain Monte Carlo, you need to formulate the model in Bayesian terms. So here's another kind of cool thing about this. You remember last time I said that, I guess I said it again, we talked about it again today, that generalized linear models are a way of, or how we do data analysis with exponential families. Markov chain Monte Carlo can be thought of as how we do data analysis with Bayesian models. Okay, remember those of you who took theory would have seen Bayes' theorem. Actually, probably anybody who had an intro probability class of any kind. If you've worked with diagnostic tests in any way, if you want to get positive and negative predictive value, those are all done with Bayes' theorem, okay? But remember, those are very simple calculations. There were no treatment effects, there were no covariate adjustments in any of that, right? As soon as you get into any of that stuff, you need some real tools to estimate those models. So a good way to think of Markov chain Monte Carlo is it's how we do data analysis with Bayesian models, okay, and Bayes' theorem. All right, so I'll talk through those. I'll set up the models. We'll talk through Markov chain Monte Carlo. We're not going to go into detail. It's it's kind of complicated stuff. So it's a little black boxy, but in a way, so this is kind of I'll just give you a preview here. It's a little bit paradoxical because actually, until you really work through a lot of the details of MCMC, it feels more black boxy than maximum likelihood, but it gives a lot more extensive diagnostics out of the box. And so I will often use it for that reason. If I can't get a model to fit on maximum likelihood, say with GlMMix or GzLMM, something like that, in SAS or R, I'll often try it with MCMC. And it gives me so much better diagnostics that I can usually see in the model where the problem is. I'll usually see that some parts are working great, other parts are not working well. So I'll show you how that works as well. And then we'll come back to this example and work through this example of Poisson regression for the serial data. All right, that's a start. Any questions before I start? Okay, you're seeing the notes, right? Okay. Okay, so in Bayes' theorem, if you remember how Bayes' theorem works, actually, I think I've got it down here. I'll just jump ahead a little bit. Here's Bayes' theorem. If you remember how Bayes' theorem works, we start with a prior distribution. So our prior knowledge about the model parameters, the thetas are all the betas and variances. Every parameter in the model goes into theta. We have a likelihood, which is the data. That's just our density, like a Poisson density. This term down here causes all the problems. I'll tell you about that in a minute. But Bayes' theorem really takes a prior, which is the P of theta, and turns it into a posterior, which is the P of theta updated using the data. Okay, so it incorporates, Bayes' theorem incorporates our the information in the data to update the estimates of the parameters. Okay, so it's a little bit of a jump ahead. But the way this works is we will get the posterior, in other words, the best estimates of the parameters using the data. The thing is, we won't get formulas for them. We'll get histograms. Essentially, that's what comes out of MCMC. We don't actually get a closed form density, but we get a histogram with as many observations as we want. So we can make means, medians, percentiles, intervals, 95% intervals, standard deviation, all that stuff's available to us. We don't have a formula, but we have enough samples to estimate it. So it's a very, very clever idea. And really, okay, so here, I want to emphasize this because this is actually, let's see, this might be the most frequent reason that I would use MCMC, even for a model I could fit with maximum likelihood. It's because as soon as you fit the model, you can get estimates for any quantity you can calculate from the data and parameters. And this is, I'll show you an example at the very end about how this works. But this is great because you remember how you have to do this with maximum likelihood? Say you get estimates of your betas for maximum likelihood, and you want to calculate a confidence interval for those of you in theory, I'll talk through just a little bit more detail. If you're not missing much, but I'll just give you a real quick summary. With maximum likelihood, you remember how you get confidence intervals for the betas? Okay, you'll get a matrix in the estimation method. In the estimation, you'll get a matrix called a Hessian. They'll invert that. It'll end up giving you an information matrix, and the diagonals of that are the variances of the parameter estimates. So you get those from the information matrix, okay? If you want to estimate a confidence interval, say for beta squared, or beta 1 times beta 2, what do you have to do in that case? There's a thing called the delta method, which allows you to do an asymptotic calculation for an asymptotic variance, okay? Well, that's all fine, but as soon as you get too complicated, you really can't do those. The value here in MCMC is that anytime you have any quantity that can be calculated from the data and the model parameters, you can get estimates. And it's really, at that point, it's just a calculation. I mean, in principle, you could do it in Excel. You're just doing calculations, okay? I mean, you wouldn't, you'd do it in RSS, but in principle, it's nothing but calculations, okay? So really valuable there. Stop me when you have questions here, and I will go ahead and illustrate some of this. So maybe what I'll do is go through this a little bit quicker till we get to the examples. This is a little sticking point. Bayesian analysis requires a prior distribution. And there's this huge controversy. It may be the main reason why there's a bit of a rift between Bayesians and frequentists, because frequentists say, well, yeah, but you have to use subjective information in your prior. And Bayesians say, Well, yeah, but you get to use subjective information in your prior, right? So it depends on whether you want to call it a problem or a feature. Either way, you do have to specify a prior distribution. I don't actually, in terms of real data analysis, I don't find this much of a limitation. You can specify a non-informative prior, which I'll tell you about in a few minutes. It's really saying you don't have any prior information about the parameters. The algorithm just runs automatically. It doesn't cause any problems. So if you don't have prior information, this is a perfectly good way to do it. And this is the way I always use it, really. I'm not what would be called a hardcore Bayesian that puts in a lot of subjective information. Okay. Maybe because I have the luxury of working with EHR data, so I usually have large data sets that don't need it. Okay, questions there? The guts of this algorithm are two steps. There's a Gibbs sampling step and a Metropolis Hastings step. Those of you who are in Nicole's class, actually I better ask that. Who, if you're in Nicole's class, have you talked about all this in her class yet? Okay, so this is kind of old stuff for some of you. Maybe you're going to see it applied to generalized linear mixed models. So you can just look at this as a nice review. For those of you who haven't, I'm talking from scratch, so you're not missing. I'm not losing anything there. So let's see. Yeah, in this Markov chain Monte Carlo refers to simulation. What that means is, as I said before, we don't get an equation for the posterior. We get a set of samples, and we can make histograms and means and intervals from those. Okay, so it's kind of a different way of thinking about fitting a model. Let's see, oh, it's a kind of simulation. Okay, but in the past, if you think about all the simulations you've done in the past, what have you always had to do? Say to simulate from a Poisson generalized linear model, you had to know all the betas, right? The key difference here is that it estimates the betas. The algorithm, in the course of simulating, estimates the betas. So that's the key difference between this and what we would usually call kind of a standard simulation. Okay, point that out. There is a large amount of user-friendly software, which, by the way, I don't know, I'm sure there's people that appreciate it more than I do, but this actually would have changed my career quite a bit. For my dissertation a few decades ago, I worked with some Bayesian models, and they were fairly complex, not overwhelmingly complex, but at the time they were fairly complex. And it was a pretty difficult slog because Markov chain Monte Carlo wasn't around at that time. And the methods for fitting those models were very painful. And I didn't need any more pain in my life. So I went in a different direction and really didn't come back to Bayesian analysis till about 10 years ago when Markov chain Monte Carlo became really common and some really nice algorithms became available. So this just can't be underestimated as how important this software is. There's also a nice paper. If you just want to read, get a really nice overview of MCMC, how it works, how it's used, this is a good paper. I don't have any connection to this paper. I just found it online by searching, but I've really thought it's a nice introductory paper, and I posted that online as well. Okay, that's a kind of a flyover. Any questions there before we start?
I was wondering, when we did this in Nicole's class, we essentially got the exact same estimates using MCMC and frequentist when we used non-informative priors. So I'm just curious, like, if there's ever times when you would expect these two different methods to stray greatly if you're using non-informative priors.
That's a great point. And I think it's actually one of the arguments that, I don't know how to say it, that non-Bayesian Bayesians, okay, so that people who are not hardcore Bayesians using subjective information can still, like me, can still justify using Bayesian models and methods. And it's exactly this. It's if you have a large amount of data, the likelihood will dominate. If you look here in Bayes' theorem, the likelihood will dominate. This will be a very sharp, a very narrow distribution. This will be a very flat distribution. When you multiply them together, you'll get something that looks very much like the data transformed over into the parameters. So yeah, I think it's a good thing. I think it's a strength of the Bayesian methods that when you do have a large amount of data, you'll get the same answers. I think the times you would probably not get the same is when you have a fairly small amount of data. And there's a couple reasons for that. One is that in that case, that's a good question. I'm having to think about this a little more than I like to in public. I don't like to think in public very much. So, but yeah, I think part of it, when you have a small amount of data, you just got a large amount of variability in your estimates. And so I think that's part of it. The other really interesting thing that happens is that sometimes it's not clear what a non-informative prior is. So for example, and I'm getting a little bit ahead here, but I'll go ahead, save us time later. For example, there's a standard prior that's used for betas in these models, and it's a normal distribution with variance 1,000 or 1,000,000, or it doesn't really matter, okay, but a huge a huge variance. What that means is that you've got a normal distribution, but it's so broad that essentially it looks flat, and it's saying your betas could be any place. If the standard deviation is 1,000, basically your parameters could be anything to your betas could be anything between -2,000 and +2,000. So very uninformative. You get over to the variance parameters, and now you could specify a prior for the standard deviation. That would be, you could say the standard deviation has a flat prior, uniform, for example, or you could say the variance has a uniform prior, flat prior, or you could say the precision, which is what Bayesians use, 1 over the variance. That's how they parameterize models. You could say that has a flat prior. Those are not all the same. So if you're being non-informative for the standard deviation, you're being informative for the variance and the precision. And that's, I think, where you would start to get into some substantial differences in results. Yeah. But I think essentially you have to have, if you have tons of data, I think you don't get into this issue.
And so if you have small sample sizes, would you say MCMC is actually more stable than frequentist?
That's a great question. And okay, so I'm thinking back to a master's thesis where we had, it was pretty interesting. It was how they count animals out in the wild. And this was kind of old, it was before webcams, but they would look at tracks in the sand and count the number of tracks. And to fit those models, they would take multiple days. So they had random effects for locations and for days. So there were 2 crossed random effects and about 50 observations. And there just really was not enough information. And so it was too complex a model to fit by maximum likelihood. But when we fitted it with MCMC, we could see that the variability for location was actually pretty well estimated. And the variability for days was very poorly estimated because we only had 4 days per subject. So we were able, I felt, to really look into the box and see where in that model was the uncertainty. So I really felt like we learned a ton from it that we wouldn't have learned, you know, with maximum likelihood. We would have gotten some, if we had been able to fit it, we'd have gotten some answers. But we wouldn't have known that we shouldn't have very much confidence in those answers. Okay? So it's a little bit of a wandering answer. But I think in small data settings, I would be inclined to even if I fitted it by maximum likelihood, I might be inclined to look at MCMC as well for that reason. Yeah. Okay, I'm going to show you some of those diagnostics in a little bit. What other question? Okay, so let's take a quick look here through Bayesian models. Thing that distinguishes Bayesian approach from other frequentist approaches is that Bayesians assume all model parameters are random quantities that have distributions. And they're, if they have a distribution, that's what we're estimating a prior distribution for. And we'll use the data to get a posterior distribution. And all of our data, so for Bayesians, the data analysis is based on the posterior distribution. That's really what MCMC is giving us. And what we call data analysis, like point estimates and confidence intervals and p-values, things like that, Bayesians get all that stuff from posterior distributions. So that's the output of MCMC as a sample of the posterior distribution. Okay, we get everything from that. Here is Bayes' theorem, which, like I say, you would have seen in any basic probability class. It's not a hard thing to calculate. The problem is in practice, this denominator here, this marginal or P of y, requires this integral. And in some cases, it's not very hard. So for example, if y is a Poisson distribution and theta is a gamma distribution, then y follows a negative binomial. So in that case, we actually have a closed form. If y is Poisson and theta is a normal or log normal, then we don't have a closed form. And that's where things get difficult. In, say, SAS-NL mix, this integral is approximated by quadrature. With basically a trapezoid rule, more complicated version of the trapezoid rule. Okay, that's fine. But as soon as you get, say, remember the model we looked at originally here a few minutes ago, it had a random effect for subject over dispersion and a random effect for family clustering. Now we have trapezoid rule going on at two levels, right? Trapezoid rule at the subject level and trapezoid rule at the family level. It's too hard numerically, can't really pull that off. And that's where MCMC comes in, is essentially to do this integral. So another way to think of it. Okay, by the way, I'm telling you some of this stuff. To use the black box, you don't really need it if the black box is working. But if the black box doesn't work, you really need to open up the hood. Sorry, that's kind of a mixed metaphor, but if you really need to get a look inside, that's when you need to know, have at least some feel for what's going on in this algorithm. Okay, so we do this by simulation. The output is a big sample of the posterior. Usually like 10,000, 100,000. You can run these things a million times. I've had cases where I had to run it, way more than 100,000 times to get stable estimates. So. But anyway, that's the output here. Posterior joint distribution. Some of this is a little technical, so I'm going to skip it here. Okay, here's priors that you've actually talked about now. Prior distribution has to be specified. If you don't have prior information, you can specify a non-informative prior. Regression, here's what I said before. Regression parameters usually assumed to be normal with a huge variance. For variance parameters, it's a lot less clear, and there's a couple papers. This GzLMM paper is my go-to source. I think there are actually updates to it now, but it's actually stayed pretty good for what now, 14 years. It's a really great paper. So I've used this. Yeah, 2,600 papers. I think that's probably up way over that by now. I think that was last year's number. So anyway, that's an issue. Another, actually, I've forgotten who asked this. this question about whether I would use frequentist or maximum likelihood. Another advantage of frequentist or Bayesian. Another advantage of Bayesian and using MCMC is you can do some sensitivity analyses with those priors. You can try a few different priors. And actually that's what we found with the animal tracks one, is that when we changed the prior much for the locations, we had about 25 locations. When we changed the prior for the random effect for location, it didn't change the estimates much. When we changed the random effect for day, where we only had 4 days, it changed the estimates a lot. So that was another thing that told us two things actually. One is that a lot of the imprecision in the model was coming from days, not locations, and we needed to be careful with the results because they were highly sensitive to that prior. So we didn't have as much precision as we thought we did. But all that we were able to see, because we were using an informative method here. Okay, any question about all that? That's kind of an overview of Bayesian modeling. Again, this is what I'm talking about today, is how we do data analysis with Bayes' theorem. Okay, so what I'll talk about, which I don't think Nicole's probably talked much specifically about anyway, is applying these methods to generalized linear mixed models. And so the models are of the form, this is exactly, so data analysis for exponential families. There's our inverse link function, our linear predictor, and our probability distribution. And the only modification we've made here is this plus use of I, adding the family clustering to the linear predictor. That's the only new thing we're talking about, but numerically it ends up being really tough. Here's the model that I had on the previous slide a little while ago. It's got clustering for families and over dispersion for subjects, both of those assumed to be normal. This model would require 2 levels of quadrature, and we're not really able to do that. By the way, just a little bit of notation. Bayesians might put betas over here as well because they're assuming the parameters are random. What's the more common notation is to put the random effects here, because these really are conditional on the random effects, but leave the betas specified. So this is a kind of a hybrid Bayesian frequentist notation here. Okay. Parameters to be estimated in this model, there's all the betas and 2 variances. MCMC provides estimates of all of those. And we'll do a worked example. This part, since you've gone over, those of you in Nicole's class have gone over this, I'm going to go through this really fast. It's too brief to add very much to what Nicole has said, and it's too brief to be very useful for those who aren't in Nicole's class. So I'm just going to mention a few words here. If you do have to read things about it, you'll have at least a little bit of a start. So we're estimating the posterior distribution. Okay, occasionally, never in practice, almost never in practice, but occasionally you will be able to calculate a closed form. That's unusual. Otherwise, we'll do things with simulation. There's 2 steps. There's a Metropolis or Metropolis-Hastings algorithm, which is what allows us to sample from the non-normal distribution. It's a clever way of kind of rejection sampling. You can sample and to get how do I describe this? It allows you to sample from a density that you can't write down, okay, in closed form. So think about this. Say you wanted to select some random gamma variables in R. What would you do? Well, you'd go find the function in R that says R gamma, okay? And you'd specify the mean and the dispersion parameter and the number of random samples you want, and you'd let it run, right? Okay. The problem is, if you don't have a density with a closed form, you're not going to have an R function that'll do that for you. And that's where we need something like Metropolis Hastings, is to allow us to sample from a density that we really can't write down. Okay, and I did find a nice, since I wasn't going to be able to explain this very well in class in the short time we have, I went ahead and found a couple of nice YouTube videos. It's what we do when we're learning statistics or fixing a stove or something like that, right? All-purpose tool. So there's a couple of really nice videos. I liked them. They're about, so I remember they're about 10 minutes long, something like that. And I thought they were nice, clear example explanations of this. So if you do want to hear a little bit more, those would be a good place to go. So that's what the Metropolis Hastings part does. It allows you to sample from a density you can't write down. Any questions or comments? So those of you who are in Nicole's class, if you want to add anything to my very quick explanations, you're welcome to. Or if I say anything that doesn't agree with Nicole, then you should probably believe her. Okay, the Markov chain part comes from, okay, you know in R, when you say R gamma, it just spits out 10,000 gammas. Okay, that's, you don't have, there's nothing fancy about it. It just puts them all out at the same time. In Markov chain simulation, it's not that way. They're done sequentially. So you simulate one value, and depending on that value, that determines the distribution that you're simulating the next one from. Then you get that next one, and it determines the distribution you're simulating the next one from. So you're working through one at a time sequentially. And that's why you'll see these time plots or trace plots that we'll be looking at in a few minutes. But that's the Markov chain refers to, is that you're going sequentially, simulation in time. Gibbs sampling allows you to use some known things. So like in the previous example we talked about with the, say, the negative binomial, let's go back up here and look at this one. For a problem like this, it would be broken down into a couple chunks. So the betas, rather than simulating for each, so Gibbs sampling, the idea of Gibbs sampling is you go through the parameters one at a time. So you'd first sample beta 0. Then using beta 0, you'd sample beta 1. Then using beta 1, you'd sample beta 2. Using beta 2, you'd sample from u sub I, or from the variance of u sub I, okay, and on and on. You can chunk it up, so you can do all the betas at once, then all the variances at once. But the point is, Gibbs sampling allows you to go through the process in chunks, and some of these chunks are pretty easy to simulate from. This old parameter, this is one of the very, very first, one of the really early applications in statistics. So you might want to be interested in seeing it just from a historical perspective, but it's also just a good example of what's involved in the chunking and writing out the simulation for these. Okay, anything here? By the way, you rarely have to do this. If you get in a really complex situation, you may need to actually write these out, and I think probably for Nicole you have done that. For most of the models we can fit, like generalized linear mixed models, there will be nice software, which I'll show you in a few minutes. Any questions on that? That was a super fast look at MCMC, but for today we're really just looking at how to use it. Any questions? Okay, so to go and do this stuff in practice, there are, actually this is where you have to work a little bit harder than with maximum likelihood. With maximum likelihood, you just specify your model and hit run, and it makes all the decisions for you, especially with generalized linear models, because it's using a canned algorithm, right? Iteratively reweighted least squares. So it's using that out. You don't have to really specify anything. Here you do. You have to specify things like prior distributions. Number of chains has to do with, okay, you could start this and let it sequentially run for 10,000 iterations. And then what you might want to do is start it again at a different place. That's the initialization, and let it run another time and then start it again. The idea there is so it doesn't, if it happens to get stuck in a local maximum, you would find out by using different initializations. Okay, so that's one thing you can do. Burn-in, you have to decide number of burn-in, adaptation, and estimation iterations. That's sort of like deciding whether you want 1,000 or 10,000 random gammas, but it's actually a little bit more to it than that. There's autocorrelation and thinning, which I'll talk about here in a minute, and then assessing convergence. So it is a little bit more work, but like I say, there's a good side to that, and that's that I can get a much better look inside the black box with MCMC. So we'll talk about each of those in the example here. Okay, for software, so the early software, the earliest probably was bugs or WinBugs. Hang on a second. The earliest versions, I think, were bugs and WinBugs. And then JAGS came along, and JAGS is virtually the same. I think of it as really the same as WinBugs. This is kind of like SAS or R. They both fit the same models. They use a little bit different algorithms. The real difference between JAGS and bugs is that JAGS was written in C++, which is a very portable language, which bugs was written in a very kind of unusual language. So it was very hard to move it from one kind of an operating system to another. That's why it's rewritten in JAGS as using C++. Then it can just be transported to any machine that can run that language. So JAGS is much more. But if you look at the code, there's only a very few places where the syntax differs. There's another approach, is I've not used Stan, a different algorithm for MCMC. The way to do these, though, all of them, by far, you want to call them from R. Or you can use SAS-proc MCMC, which actually works pretty well. And I've posted an example of proc MCMC in the notes online, so you can take a look at that. There's a lot of, I don't remember if I posted the user's manuals for bugs and JAGS. They might be there, I don't remember. Anyway, they're very easy to access. Oh, and there's kind of a cool follow-up paper about 10 years after bugs, after they put out the original bugs. They got together and kind of did a retrospective and say, what do they like and what do they not like? So if you're interested in, say, data science and computing and stuff, this is a fun read. Okay, any questions on the software? Just final warning here, I'll ask for questions again in a second, just final emphasis here on this, that MCMC software is more complex. You need to specify more things than maximum likelihood, but it also gives more extensive output, and you can get a much better look at what the model's doing. So when somebody comes to me saying they can't get their model to run in GlymMix or NLMixed or something, I would usually say give it a try in MCMC, because you'll probably be able to see where in the model the problem is. Now, any questions? Okay, well, let's take a look at some of this output. There's trace plots. I'm just going to go just breeze through these, and then we'll take a look at examples. Trace plots are just a plot of the simulated values in time order. Since these are Markov simulations, the time order does matter here. So you can really learn a lot by looking at them in time order. We'll look at some examples of where they look good and where they don't look so good down here below. Model fit, there's similar things to AIC and BIC. These are called the DIC for deviance information criterion. Same thing, smaller is better. There's a number of convergence diagnostics. This is a little bit, well, no, that's not quite. I don't know that there's a correspondent in, say, linear regression to this. I think this is kind of just a numerical diagnostics, but several of these I've listed here. And then as far as reporting results, here's an example from an old paper Matt and I wrote together. on his asthma inhaler stuff, talked about chains. There's the length of the chain. That was a fairly complex model. That had about 100 and some kids, each one observed for 122 days, had some missing data, had some autocorrelation, had some clustering. So there was a complex model. We had to run that 100,000 iterations in order to get it to converge. I've had models where 100 iterations was plenty. For a simple model, 100 might be plenty. For a complex model, 100,000 may not be enough. So it's really the number of iterations is very problem dependent. Let's
Out of
see.
curiosity,
Sure.
how long does it take to run for 100,000?
Oh, that's a great question. Yeah, it depends a lot on the computer. At that time, this was about 10 years ago when this was being done, and I would have done it on probably a Dell laptop. And for 100,000, as I remember it, it was on the order of 3 or 4 hours, something like that. Yeah, so it's not trivial, but you know, I can sleep fine while my computer's working. And I would never personally trade. So, you know, another thing you could do is try to write. Okay, so one thing probably would have sped it up is if I had written the algorithm in, you know, C or something like that. Okay, but that involves trading brain power for computing power, and one is very, very limited. And the other, there's pretty much plenty of. You do hit the wall sometimes, but if I can solve the problem by with a good night's sleep and wake up in the morning and it's solved, I'm perfectly fine with that. But yeah, it is a thing to consider, and it was. By the way, I shouldn't probably minimize this because it's not like I just set it to run. The next morning it's all fine and that was it. There was a lot of fine tuning. There was a lot of, you know, getting out the bugs and stuff. So I don't want to minimize the hassle that this can be. But usually if you're going over here and you have a fairly complex model, it's worth the trade-off. For the kind of models we're talking about, say a negative binomial with clustering, that would run now on my laptop, would probably run in a few minutes would be my guess, for, you know, hundreds of subjects and, you know, 100 observations or something like that per subject. Okay, great question though, yeah. What else? Okay, so we talked about some stuff here. Okay, estimate, parameter of interest. So all these numbers here, let's see, okay. Yeah, all these numbers here, the beta hat, the standard error of beta, instead of a confidence interval, it's called a credible interval. Here's the interval. All of these numbers here were calculated from the 100,000 values up here. Just basically calculated the mean of those, and that was the 1.0128. Calculated the standard deviation of those, that was the 0.0083. Calculated the 2.5 and 95 and 97.5 percentiles of these 100,000, and that was the interval. Okay, so once you've got the sample, it's all very easy. Any question on that kind of stuff?
So I haven't taken Nico's class, but once you have all the samples, are these confidence intervals just using like normal theory and like Z distributions and stuff?
No, good question. They're actually, so this one is assuming that the histogram of these 100,000 values is normally distributed, and that you can basically use the 95% rule, saying the mean plus or minus 2 standard errors or standard deviations. Since these are samples of the beta hats, these kind of correspond to the standard errors, but that you can use the 95% rule on this. So this number here is assuming the normal approximation. In other words, assuming these are normally distributed. Not the data, but the samples. Okay, so you've made your histogram, you've got all your samples, made your histogram, and that's what it looks like. Down here, This is not. This is percentiles. So if this is a highly skewed distribution, these percentiles will take that skew into account. So that's actually an advantage here because you don't have that option with maximum likelihood. Okay. Well, what other questions? Okay, so let's get into this Poisson example. Here's our Poisson generalized linear model. Here's the maximum likelihood fitting. We've specified the linear predictor, the distribution, and the link function. Here's some estimates. Here's some confidence interval stuff. Exponentiating the betas is giving you the rate ratios. Okay, so these are just for, we've done all this before. This is what we did last time. Here's how you do the same thing in in JAGS. First, I'll have you note, the code is not much longer, right? And most of this code here is all specifying priors. So really the code here is just the same thing. Here's your link function, here's your Poisson distribution, and here's your linear predictor, okay? So it's not like this is so overwhelmingly complicated you have to take a whole semester class on it. This is totally doable, right? For you guys can now go away and fit these models. I could, Matt wouldn't let me give any homework, but if I had, I would have asked you to give things like this, and it would have been would have been about as hard as your last homework assignment on generalized linear models. Okay, so it's not like this is out of your range, totally in your range. Okay, specify some initial values and such. And then here's the summary stuff. I'll let you read through in detail, but again, we're exponentiating the percentiles of this distribution. And I think I have, okay, so I'm going to give you a bit of stuff on diagnostics now. This is what you get out of MCMC. Here are four model parameters, 4 betas. First, I ran it with no burn-in and no adaptation and some fairly lousy initial values. And here's what happened. It found its way to the solution, but it took a little while. Not a long time, about 50 iterations, so I remember maybe 100 iterations, something like that, to get into steady state. So it did converge, but it took a little while. You would not want to use these iterations in getting your means and standard errors, right? And percentiles. These are not useful. They're not fitted values. They're converging values, okay? So second one, you let it adapt for 100 iterations. And now you can see, in this case, now you can see it still looks kind of stringy. It's certainly better, and it's not trying to find its steady state yet, but these are still kind of unstable. I wouldn't really want to use these for estimation. So then I let it adapt more and ran it for more estimation iterations. This is what you're looking for here, okay? Would you trust that the mean and percentiles of these distributions give a good representation of the distribution? Absolutely. I'm completely good with this. Okay, they're a little bit correlated. That's okay, because if you've got a lot of them, that correlation evens out. Okay, so these are the trace plots. These are your diagnostics. If you see one of these parameters looking terrible, the others look great, that's how you tell that that's the part of your model that's unstable. That's where the problem is. Okay, that's how you can use these diagnostics. I don't think I have a good example of that here. Any questions on how to interpret these? Okay, for estimation, you just make a histogram over here, take the mean, the standard deviation, the percentiles, and there's your estimates. Here's the maximum likelihood, here's the MCMC, and as I've forgotten who said at the beginning, or in the middle here someplace, these are very close for maximum likelihood and MCMC. Got a good sized data set here, so not a big issue. Any question on this? Okay, so that's a very simple model, which we could easily fit in maximum likelihood. Here's the next model we'll look at. This is a serial data again. So I'm doing the homework I would have given you. If I was going to give homework, this is what I would have given you. So this is the Poisson generalized linear model with over dispersion. So here's your linear predictor, your link function, your distribution, and here's the plus E sub I for the overdispersion. So this is the additive random error method for modeling overdispersion, assuming it's normally distributed. There's no closed form for this, so we would have to do numerical integration like quadrature if we do maximum likelihood. And in SAS, GLMER will fit this model. Here's the specifying of the random effects. It's a little tricky here with overdispersion because remember you have a different epsilon for each observation. This is not family clustering yet, okay? But we're still using the same device of a random effect. Okay, here's the output, just like we would usually see. Here's the exponentials of the betas. Here's the edges of the confidence intervals, okay? Nothing new there, all the kind of stuff you've seen before. And there's the result, the estimate and the confidence intervals. Question on that? In SAS, that would be done by proc NL mixed. In fact, I think you did that. I think for your first homework, you fitted this exactly this model. Okay, so let's do the same thing in JAGS. So here's the plus epsilon. We don't have many modifications to make. We have to specify there's a random effect. That's normal. We have to specify priors. Okay, so this is slightly tricky. Bayesians always parameterize in terms of 1 over the variance, what they call a precision. So that's tau. And then the variance, so the standard deviation is the, sorry, we're going to put it, so this, in this case, I've decided to put a uniform prior, an uninformative prior on the standard deviation of the random effect. And that's not exactly what Gelman recommends, but it's fairly close. Tau then is just a transformation. It's just 1 over sigma squared. So we've done that. But look, the modifications you had to make to the JAGS code for this model are pretty slim. We really didn't have to do much. Here's your run JAGS. Here's the function in R that runs it. We'll get some output. Let's look at some trace plots. Okay, we have one more trace plot, right? Because there's one more model parameter. Notice the variance is being, the standard deviation is being estimated at the same time as the betas. Here's your output. That one looks perfectly fine. I totally trust that standard deviation estimate. Here's the lower, median, upper, mean, and standard deviation. Nice function in R to get those. So here's the 4 betas and the standard deviation. Okay. So this sigma E is the standard deviation of this normal distribution. It's sigma sub E. So we've got all our model parameters estimated. The trace plots look great. And now here's a summary of everything. So here, these first 2 are the Poisson, second 2 are the overdispersion. And as you can see, in this case, the overdispersion did not do much to the estimates, which I've found in practice is usually the case, but it did widen out the intervals quite a bit. 1.8, 1.8 to 3.1, 1.6 to 3.5. So the intervals here are quite wide, quite a bit wider. They're not much different. Again, we were able to fit this model with maximum likelihood, so we can do the comparison. They're a little bit different, but not a whole lot different. Usually what I see is that the intervals for maximum likelihood, for MCMC are a little bit wider than maximum likelihood in cases where I can use both methods. And the reason for that is that the MCMC is able to take into account the variability in the estimate of the variance parameters, take that variability into account in the estimates of the betas. It's not possible to do that with maximum likelihood. Maximum likelihood conditions on assuming the estimated variances are fixed known values. So that means their intervals are a little bit wider. So my MCMC is slightly more conservative, or more correct, as Bayesians would say. So I believe that's it on this. Any question on any of this? What if we wanted to add family clustering to this? What would we do? Well, that would be slightly more complex because we'd have to have two subscripts. We'd have to have I and J because we'd have to keep track of what family they're in as well. We'd end up down here with a plus E, a plus U sub I and a plus E sub IJ. Okay, but it really would be basically the same thing. The advantage would be over maximum likelihood would be that we could do it. The disadvantage of maximum likelihood is with two levels of random effects. SAS claims NLMix can do it. I spent a huge amount of time trying to figure out, and I never had one successful model fit, which I agree might say something about me instead of NLMix, but I think it's a lot easier than they advertised. What questions do you have now? I want to show you one more example, but if you have any questions on this, let me know. Okay, I want to show you this very briefly because it is, again, one of the big advantages of MCMC in a case like this. And this is something we do at our VA group quite a lot. Say you have a set of hospitals. The VA has about, we used to do cardiac surgery, so a lot. And so we usually have about 60 some hospitals. And people want to know, are any hospitals unusual in the sense that they have more or fewer events than expected? And those events might be might be complications, might be deaths, might be costs. We do this a lot for costs, which hospitals have the highest cost or lowest cost. So really, this is a case where you would fit, if you sorry, I'm not sharing, am I? My mistake here. How do I get back to that? Yeah, so for identifying hospitals, you would use, to model it, it's not a very hard model, you would use, let's say you have a binary outcome, you would have J patients in hospitals, I hospitals, say you have a binary outcome for mortality or something like that, you'd use logistic regression with a random effect for hospital. Everybody okay with that? You would have seen that in Matt's class. You saw it, I think, from me a couple of weeks ago. Okay, so nothing new here. We fit this model. You've got patient covariates with IJ, hospital covariates with subscripts I. Nothing new with any of those. Okay, random hospital effect. Okay, you could fit this in SAS, GzLMM easily, or NLMix, no problem. The problem is, when you come to specify the results, it's really not very useful to say, well, the log odds of some hospital is something. That doesn't really tell you much. It's not really useful. So the standard way of doing this is to use some counterfactual arguments and say, we're going to calculate the expected mortality at a hospital I compared to the expected mortality if they had an average mortality. In other words, if their random effect was 0. Well, look at this calculation. It's not a very hard calculation to do. You could do that in R quite easily. It's a few statements. What's the problem? The problem is, how do you get intervals for that? How do you get your credible intervals or confidence intervals to identify, okay, here's, I didn't show you a good one with the lines, but here's an example of a hospital that's shown its interval. And that was identified as a high cost or high mortality, I've forgotten. The point is, to get that interval requires calculating the 95% bounds on this quantity. Look at how complicated it is. It's got alphas, it's got estimated random effect, it's got covariate values in there, it's got a sum, it's got a nonlinear function, it's divide. Okay, you're not going to be able to use delta method or any other analytic method to get intervals for that. How would you do that with MCMC? Well, you've got 10,000 values from the posterior density for each of these parameters, right? So do this calculation for each of those 10,000 values, which is very easy. Make some histograms, calculate means, calculate 95th percentiles, 95th percentile ranges, and there you go, okay? So with MCMC, this is very easy to do, to get these displays, to get the inference, to identify unusual hospitals. The only way to do it with frequentist methods is bootstrap, which, okay, you can, but this is kind of what's designed for this approach. All right, so there's an example of a time when I would definitely use MCMC. So what questions do you have? Anything? We're out of time here, but I'm happy to stick around a few minutes if people have questions. Okay, well, I hope I've conveyed over to you that this is super useful. It's a very cool stuff because, like I say, it gives you a way to do data analysis with Bayesian models, but the range of models that can now be fitted with this is just so much greater than MCMC. So this should be definitely in your toolbox, and you absolutely have the ability and some examples to be able to fit these models. So, okay, that's the final message. If you want to give this a try and need some help, don't hesitate to reach out. So otherwise, been good seeing you all. I think I'm done for the semester, so turn you back over to Matt, but nice to see you all again.